Okay, so previously we were talking about the chapter congruences on integers. We've defined the congruences, then we have given some propositions, then we have talked about arithmetic with congruences, how we add and multiply them, and then we have defined the way to solve the congruence equations. Okay. Now, the topic is going to be, in this part, the system Zm. Now, the properties of congruence modulo M can be encapsulated rather neatly by defining a new system denoted by Zm, which we can think of as the integers modulo M. Before defining this in general, let's talk about an example, and we will understand that by this example. So we are saying we have an example. (13.8) which says that let's take M is 4 and let Z4 the set of consisting 4 integers. So this is a set which consists 0, 1, 2, 3. We have talked about it before in previous lectures. And define addition and multiplication of any two numbers in Z4. So let's say define addition and multiplication in Z4. To be same as integers, except that we make sure the answer is again in Z4. Except that we make sure the answer is again in Z4 by taking Congruences modulo M4. Perfect. For example, let's add 2 plus 3, that is 5, in Z4. But the number 5 is not in Z4. So this is congruence equal to 1 mod 4. So 2 plus 3 in Z4 is 1. Here are some other examples. So let's say you have 1 plus 2, which is 3, and it is in Z4. 0 plus 3 is 3, it's also in Z4. Now 2 plus 2 is 4, and this is going to be modulo congruent to 0 mod 4. Okay, so this is also in, so now 2 plus 2 is equals to 0. So you can say 2 plus 2 is equal to 0 in Z4. Similarly, 3 plus 3 is 6, which is congruent to 2 mod 4. So 3 plus 3 is 2 in Z4. Now the multiplication, and 0 multiplied 3 is 0. 2 multiplied 3 is 6. Now we have 6 here. So this is again equals to 2 in Z4. 3 multiplied 3 is 9, which is congruent to 1 mod 4. So you can say 3 multiplied 3 is 1 in Z4, and so on. So the full addition and multiplication tables for Z4 are as follows. So the full addition and multiplication tables for Z4, okay, are as follows. So let's say we have table which is plus, and then we are saying this is 0, 1, 2, 3. This is 0, 1, 2, 3. Now, if you add 0, 0, that will be 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 1 plus 0 is 1. 1 plus 2 is 1 plus 2 plus 0 is 2. 3 plus 0 is 3. Okay. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. And 4 in Z4 is 0 again. Perfect. Now 2 plus 1 is 3. 2 plus 2 is 4, which is 0. 2 plus 3 is 5, which is 1. Then 3 plus 1 is 4, which is 0. 3 plus 2 is 5, which is 1. 3 plus 3 is 6, which is 2. This is under addition. Similarly, we can write something under multiplication. So obviously, multiplication by 0 of every number is 0 again. 1 multiply 1 is 1. 1 multiply 2 is 2 and 3. 2 multiply 1 is 2. 3 multiply 1 is 3. Then we have 2 multiply 2 is 4, which is 0 again. 2 multiply 3 is 6, which is 2 again. 3 multiply 2 is 6, which is 2. 3 multiply 3 is 3 multiply 3 is 9, which is 1. Okay. Perfect. So these are the tables for addition and multiplication in Z4. So let's define this system. In general, for a fixed positive integer m, the system, let me just increase the brightness a little bit more. The system Zm is defined in an entirely similar way. We take Zm to be the state consisting of m integers and those are 0, 1, 2 up to m minus 1, and define addition and multiplication of any two numbers in Zm to be the same is for Z, except that we make sure the answer is again in Zm. Except that we make sure the answer is again in Zm by taking congruences modulo m. Okay, so let's define this more formally. For x comma y in Zm, the sum and the product of x and y in Zm are defined to be the numbers k comma l in Zm such that x plus y is congruent to k mod m and x into y is congruent to l mod m, respectively. And we will write x plus y is k and xl is l in Zm. This is how we define the system Zm in general. Now, let's talk about some other example in the sense. So, for example, in Z5, we have 4 plus 4 is 3. And in Z7, we have 5 cross 3 is 1. And in any way, and in any Zm, m minus 1 plus m minus 2 is m minus 3, and m minus 1 to m minus 2 is 2. Now the system Zm is quite useful. It's quite a useful one. We can do quite a bit of algebra in it, such as taking powers and solving equations. So let's try some examples to understand it more. So we define, let's say we have an example 13.9. Number 1, we can define powers of elements of Zm in a natural way. So for x in Zm and r in the natural numbers, the rth power of x in Zm is defined to be the number k in Zm such that x power r is k mod m. That means, for example, in Z5, we have, so remember Z5 have these following elements 0, 1, 2, 3, 4. And yeah, at this level, we can only consider them as an elements in the state, but like actually, they are not only the elements, they are itself the classes, equivalence classes, if you know about it. So each element in this set is an equivalence class, and each element in this set have their own kind of elements. So in Z5, we are saying if there is 0, we are saying all those elements whose remainder is 0 if we divide by 5. All those elements whose remainder is 1 if we divided by 5. So the first element in this one equivalence class is going to be 6. Then it's going to be 11. Then it's going to be 16 and things like that. Similarly, we have the first element for the second two equivalence class is 7. Then we have like 12, something like that. Okay. So now let's try something, the powers, and we have these elements in Z5. So you can say that 2 power 2 is 4, which is in Z5, but 2 power 3 is 8. And if you see 8, And if you want to see 8 in Z5, just divide it by 5, you will get the remainder 3. So this is nothing but 3 in Z5. Similarly, we have 2 power 4, which is 16. And as I told you, 16 belongs to the equivalence class 1. So it is 1 in Z5. This is what we meant. Okay. Now, similarly, we have done an example. So example 13.2 and 13.3 show that in Z7 we have 6 power 82 is 1, while in Z13 6 power 82 is 4. Previously, we have talked about these two examples, and then we have solved it for Z7 and solved it for Z13. And we have these two different answers for a similar number. So it depends on the system like Z7, Z5, Z13, in which you are working on. Okay, perfect. Example 2 says like proposition 13.6 tells us that for any tells us that for A comma B in Zm, the equation Ax is B has a solution for x in Zm if and only if this IFF means if and only if HCF of A comma M divides B. That means that you can only solve a congruence equation if you have an equation Ax is B if and only if A and M have some HCF that divides B. Okay. So for example, the equation 2x is 7 has a solution in Z9, namely x is 8, but not in Z10. Okay. Similarly, example number 3 says that the example we have discussed before is 13.4 and 13.5 in this chapter show that the quadratic equation x square is 2 has no solution in Z3 and x square is 3 has no solution in Z4. So in general, to see whether an equation in a variable x has a solution in Zm, an equation in a variable x has a solution in the system Zm. Unless we can think of anything better, we can always just try substituting each of the m possible values for x and seeing if they work. So Zm, unless we can think of anything better, we can always just try substituting each of the m possible values for x and see if they work. So let's say, for example, does the equation x squared plus 3x plus 4 is 0 have a solution in Z5? So, well, if we substitute the 5 possible values for x into the expression and work out the answers in Z5, here is what we get. So let's write that procedure. So if we substitute the 5 possible values for x into the expression x squared plus 3x plus 4 and work out the answers, in Z5, we will get that we have x 0, 1, 2, 3, 4. So let's say the equation is x square plus 3x plus 4. So if we put x 0, we will get 4. If we put x1, we will get 3. If we put x2, we will get 4. If we put x3, we will get 2. If we put x4, we will get 2 again. So that means the answer is no. There is no solution in Z5. Why? Because they are supposed to be at one value, they are supposed to be equal to 0 in this column. In this column, so in this row, they are supposed to be equal to 0. Okay? So there is no solution in Z5. However, this equation does have a solution in Z11. So let's try that. X 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now Z11 have all these values. And then we have an equation x square plus 3x plus 4. Okay. Now let's put 0, that will be 4. Let's put 1. 1 plus 3 is 4, 4, 4, 8. Okay. Let's put 2. 2 square is 4. 2 into 3 is 6. 4 plus 6 is 10. Plus 4, 14. 14. So if you divide 14 by 11, you will get 3. Okay. Again, let's put 3. 3 square is 8. 3 into 3, 9. 9 and 8, 17. 17 divided by plus 4 is what? 21. So 8 plus 9 is 17. 17 plus 4 is 17 plus 4 is 21. 21 divided by 11 is what? 21 divided by 11 is 9. It's 10. Okay, let's put 4. 16 plus 12 is 28. 28 plus 4 is 32. So it will go 11. 2 times 11 is 22. And then again, you will have 10. Okay. Now, 5. 25 into 15, that is 40 plus 4, 44. And if you divide it by 11, you will get 0. So here we go. I have a doubt on 3, but like 5 is certainly a solution in Z11 for this equation. So you can say x is 5 is a solution for x square plus 3x plus 4 in Z11. Okay, perfect. We will end this lecture over here.